Okay, hello everyone. This video I'm going to demonstrate one of your homework problem. This problem, yeah, I think maybe you will feel it's kind of difficult. So I just want to make a video. So I want to make a video to make some explanations. Yep. Okay. Yeah, it's because it's combined to the yield stress. Okay. Okay, so this is the problem I want to demonstrate is 937. Okay. You say there is a 10 millimeter diameter steel bolt. Okay, and the bolt, I think in this graph, the bolt is here, okay, right at the center, and it's blocked by, bracket by the dash line, okay. And this steel is a cylinder shape, and then there is called okay, sleeve, a sleeve surround the bolt, okay, and the bolt is made of steel, okay, and the sleeve is made of bronze, okay, and the outer diameter of the sleeve is 20 millimeters. So yeah, just let me draw the picture. So it just look like this. Okay, I think you really need a. Mm, okay, so this is the problem description. Okay. So he said this is a coaxial system. So the coaxial is look like this. So it's look like here is a coaxial system. It's coaxial. Coaxial. Okay, if you don't know coaxial, 中文 means 同轴. Okay. Okay, coaxial. Okay, and the coaxial, the sleeve is made by bronze, and so that means the shell is made by bronze, and the core is made by steel. Okay, and the outer diameter is 20 millimeters, so that means this is 20. This is 20 diameter. 20. This is 20 millimeter, and the inner diameter is 10 millimeter. Okay. So that's a top view of the coaxial structure. Okay. And in this problem, he give you the yield stress. Yeah, it's kind of special. He give you the yield stress of the steel is 640 megapascal, and the yield stress for the brass, or not the brass, bronze. Yeah, maybe I just make some spill. Yeah. Okay, it's bronze, not brass. The bronze. Okay, the yield stress for the bronze is 520 megapascal. It said determine the largest magnitude of the external load P that can be applied to the assembly, and also give you the elastic modulus of steel and elastic modulus of bronze, 100 gigapascal. Okay, so the problem is want to find the magnitude of external load P. Okay, so let's look at this coaxial structure. Actually, this problem is very similar to, okay, this problem is very similar to example 9.6, and I had already made the video for example 9.6. You can look it up. Okay, go to find the video to look at this video. Yeah, I won't repeat this example one more time. Okay, so actually this problem is related to statically indeterminate. Okay, so let's first of all, okay, so it means, okay, so it says, okay, we have a coaxial structure, okay, and we have apply external load in the P to the coaxial structure. Okay, coaxial structure, and okay, coaxial structure, okay. And then we just, okay, we make a cut section here. We made a cut section here. Okay, because we apply an external loading here, there must be some internal load to make the whole system static. So if we cut a section here, so there must be some internal normal force to resist the external load. Okay. Okay, so, and the most important thing here is Okay, because this is a coaxial structure. Coaxial structure. The bronze part and the steel and both contribute to the normal force. Mhm. Okay, so this coaxial structure, the steel part and the bronze part also contribute to the normal force. That means, normal force we have two parts. It's bronze or use BR, small BR contribute normal force. BR part contribute normal, steel part also contribute to a normal force. Okay, okay. So that's the first important thing. Okay, and then we cut section here. We cut section here, so we can do a rigid body equilibrium on this cut section. Okay, so rigid body equilibrium. What will we have is what will we have? We will have this n point up. So n minus p point down equal, so it's minus, so equal to 0, and n equal to nbr plus nst. So nbr plus nst is equal to p. Okay. Okay, so the problem want us to determine the largest p. Okay, largest p. Okay, so that means we have to figure out the normal force on bronze and normal force on the steel. Okay, add them together and we will have the p. Okay, so actually this problem just want you to calculate the normal force acting on the bronze part and normal force acting on steel part. Okay, so do we have any equation to, yeah, this is, we use a rigid body equilibrium. Yeah, but right now we cannot solve the problem. Why? We cannot solve the problem, okay, because there are too many unknowns. We just only have one equation, so we cannot solve like NBR, NST. So again, so this is it is look at, and this problem is looks like a statically indeterminate problem. And in this coaxial system, I have to already tell you the competitivity equation is, because it's a coaxial problem. So when you compress this rod together, so this coaxial structure in this coaxial structure, the steel part and the bronze part have the same deformation. The steel part and bronze part has the same deformation because of this coaxial structure. And you push this rod, these two parts will have the same deformation. Okay, so what can we express this is in mathematics? Okay, so that just means okay, the bronze part deformation bronze part equal to the deformation at the steel part. Okay, and this is the axial loading system. So do you remember how to calculate the deformation for axial loading? So you remember that it's equal to normal force times L divided by E times A. Okay, so this detail we need the okay normal force at BR part and length of BR part, and also divide the EBR and times the ABR, and equal to N ST times L ST E ST and A ST. Okay, and so in this coaxial structure, the bolt and the bronze, sorry, the bolt and the sleeve has the same length. Okay, so we can just cancel this out. Okay, and do we know the information of the elastic modulus of bronze and steel? Yeah, we have. We have, because this give us. And do we know the area of the bronze and the steel part? Yeah, it gives us a diameter, so we can calculate something. We can calculate some parameter first. Okay, so so that's the so ABR is BR, because be careful because this BR, only this region is BR, so you need to use the circular formula. So you have DO squared minus DI squared. Okay, don't forget how to calculate area for a circular shape. Okay, so what's the value? Okay, pi over 2. So D is 20 millimeter square minus 10 millimeter square. And okay, so and what about the AST? AST is much easier. So it only AST only is here. So it's 10 times 10 to the power minus 3 square. Okay. Okay, so what's the value? Okay, so if you use your calculator correctly, sorry, this is not 2. Sorry, because this diameter, this should be 4. Okay, it should 4, 4, 4. Yeah, really, you have to really careful for using the formula. Really, really careful, or you'll get a totally wrong answer. Okay, pi r squared. Yeah. Okay. So first of all, what's the area for the steel part? So if you will calculate directly using your calculator, you will have this value. Okay, and what's the area for the bronze? 2.355 times 10 to the power minus 4 m squared. Okay, so we just calculate using this formula to calculate the area for bronze part and area for steel part. Okay, so we keep this information. Okay, so let's us keep information here. Okay, because I'll erase this 2.355 times 10 to the power minus 4 and let's keep the information here because I'll erase this two. I'll erase this part. Okay, so we will have the elastic modulus for steel and bronze. So I don't. Okay, you just don't have to take notice because this is a cleared state. Okay. Okay, so we will have an equation like this. Okay, we will have equation like this. Okay, so that's a start. Keep continue. I think we are going to have the answer quickly. So we will have the MBR. Okay, so EBR times ABR. EBR is 100 gigapart. And what is EBR? What was ABR? ABR is 2.355 times 10 to the power minus 4. Okay, and equal to the NST. And EST is 200 gigapart. And times what's AST? The area for steel, 7.85 times 10 to the power minus 5. 85. Oh, okay. So we will have keep simplification. So what's the denominator? Yeah, actually we can denominator. Okay, we can have the denominator first. Okay, let me see. I think if you use calculator, right? So we have this 2355000. Okay, and this is NST. So what's the value here? So it's 1570000. 50 let me check. I'm checking my notes. Okay, so what would this tell you? So 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Okay, what would this tell you? Okay, so this tell you MBR is equal to, okay, we have to times, okay, 2355000 divided 1570000. So 1.5, really? 1.5, really? 1.5, 1.5 NST. Okay, really? 2355000 157. All right, 2355000 divided 1570000. 1.5. Okay. Okay, so we use the competitivity equation. We got this relation, and the normal force of on the bronze part is 1.5 times the normal force at the steel part. Okay, so we once again we keep this information. Okay, we keep this information. So let me erase this part. Okay, let us keep this information, and I'll erase this part. Okay. So I'll keep this info. We'll keep this information. I'll write the information here. So here's MBR equal to E 1.5 and still. Okay. So what's the next? Okay, no, next we have to discuss. Okay. So this problem give you the yield stress of a steel part is 640 megapascal. And for bronze part, for bronze, the yield stress is 520 megapascal. So in previous lecture, I already tell you the yield stress is kind of limit, okay, kind of limited for the material, elastic limited for this material. After the yield stress, we consider the material is fail. So the yield stress is a kind of standard for the failing. Okay, before smaller than yield stress, the material is fine. It's greater if you apply if the stress normal stress is greater than yield stress, the material is fail. Okay, so how to relate it to this problem? Okay, the problem want us to determine the maximum loading P. Okay, you can see here. Okay, even if we put this here in put this relationship in here, we still cannot solve P. Okay, so how to solve this P? So you have to. Okay, so let's first of all let's do something about this yield stress first. Okay, the yield stress actually that just means it's a standard for it's a criteria for failing. So that means if the yield stress for the steel is this value, so what's the maximum normal force for steel? What's the maximum normal force in steel? So what's the maximum normal force? So I still call it Y. What's the maximum normal force for steel? So actually is the normal stress times the cross section area, right? Times the AST. Okay, so what's AST? So times AST. Okay, so times AST. Okay, so okay, AST is 7.58 times 10 to the power of 5. Okay, so if the yield stress is this, so what's the normal at this yield stress? What's the normal force? Okay, 6 4 times 10 to the power minus 6 times 7.85. So so let's see. Okay, so it's 50240. So it's 50240. Okay. Okay. So let's first try this. Okay, if we try the limit, okay, try the limit on steel first. We try the limit on steel first. If we try the limit on steel first, that means the yield stress. That means the normal force will be 50240 Newton. Okay, and that means and then we put back into this equation. That means the maximum. That means the normal force for steel at this situation. Okay, if we test the steel as a yield stress and at this geometry condition, the steel part will have 150,240 Newton normal force, and then we put back into this equation. That means your bronze part will have a normal force because for this 5 times the 1.5. Okay, so times 1.5. 75360 Newton. Okay, and then let's try. If at this condition the normal force on the bronze is 75360 Newton. Okay, and then at this condition, what is the normal force for bronze part? So the normal stress equal to the normal force divided by cross section area. So ABR. Okay, so what's our ABR? ABR is 2.3055 times 10 to the power minus 4. Okay, so what's this value? Okay, so what's the shear stress right now? So not shear, not what's the normal stress right now? Like, yeah, I keep mixing up. So 3.2.355 10 to the power 4. Okay, and by power 6. So it will be 320 megapascal. Okay. Okay. So let this calculation just mean, okay, right now if we try the limit on the steel, try to limit the shear stress on the steel. Okay, because the yield stress is the limit, the highest limit of limit for this material for steel. If we try the steel limit 600 megapascal, and then we'll have the normal stress at the bronze part is 320 megapascal. And the 320 megapascal, you will see this 300 megapascal is smaller than the yield stress of bronze. You see that? You see this connection is smaller than, maybe I move this here. Okay. So it's smaller than the yield stress for the bronze. Yield stress for the bronze. Okay, what's the value? 520 megapascal. Okay, and just I said at the beginning, if a material is subject to the stress under the yield stress, that means your material is at the elastic region, and elastic region, that means it can restore. Okay, so that means it's in safe area. It's not failing. Okay, so in this calculation, if I try the limit for the steel. Okay, and at this limit, the bronze will still in a safe, and the bronze is safe, not failing. So this is okay. This is okay. Okay, so and then don't forget what's our purpose of this problem. We want to find the elastic loading. We want to find a P. Okay, what is our P? Okay, so it's N normal force bronze part and add the normal force on steel part. So at this condition, it's okay. So we have to add these two together. Add these two together. So you add these two together, I think the value will be, let's say, I think it's because 125.6 kilonewton. Okay, so at this condition, okay, at this condition, the loading is 125.6 kilonewton. Okay, okay, it's fine. So let's keep this answer. Okay, 125.6 kilonewton. Okay, and at this condition, we apply the stress. We apply the yield stress on the steel 640 megapascal. Okay. Okay, this will give you the total load 125.6 kilonewton. And it's okay. Okay. Okay, so but we only try this one limit here. We have to try the other limit. Okay, if we try we try on steel. Okay, we'll try the same procedure, but we try a limit on the bronze. Okay, so I will do the same procedure, but I don't have space here, so I have to erase this last of this part. So if you want to take notes, just please stop or rewind. Okay, okay, so let's try another. Okay, so we will try it for bronze. So we'll have this for bronze, and yeah, this will be different. This will be different. This will be different. This different. This will be different. This will be different. This also different. This will be also different. This will difference. Okay, this will be different. This is different. Different. So there's difference. Okay, we try another limit. The other limit is the bronze 520 megapascal. 520 megapascal. Okay, on the bronze. And that means what's your normal force? Okay, normal force for the bronze. Okay, so actually just use 520 times to 10 to the power 6 and times the area for the bronze. Okay, so the area for the bronze, I think we have calculated this before. Oh, okay, so I think for bronze, okay. Oh, do I calculate it right? HST still, did I calculate it right? Still? Mm-hmm. Okay, maybe I calculate so. Okay, bronze is 2.355 10 to the power minus 4. Okay, so what's the normal force now? So 520. 355. Okay. Okay, so that will give you 1222460 and Newton. Okay. And what's your normal force on the steel? What's your normal force on steel? Okay, don't forget this equation from the competitivity equation. We have the normal force for the bronze. Okay, so what's our normal force for steel? It's just this value divided by 1.5, right? So divided by 1.5. So it's equal to 81640 Newton. Okay, at this normal force, what's the normal stress for steel? What's the normal stress for steel? Normal stress for steel. So it's just a normal force divided your area of the steel. So what's the area of steel? The area of steel we already calculate. Area of steel 7.85 times 10 to the power minus 5. Okay, so divided by 7.85 and times 10 to the power minus 10 to the power 5 divided by the power 6. So it will give you 1040 megapascal. Okay, and what's the yield stress for steel? What's the yield stress for steel? What's the yield stress for steel? Okay, what's the yield stress for steel? Well, the yield stress for steel is 640 megapascal. It's 640 megapascal. So actually, the value we calculate 1040 megapascal it's greater than yield stress of steel. Okay, so that means another limit in this limit, the steel fail. Still fail. Okay, still fail. Okay, so that means at this limit, at this min limit, the still fail. You apply this normal stress on bronze part, it will cause the fail of on the steel. Okay, so the materials fail. So we don't consider this as the largest elastic in load. Okay, because if you add this together, these two values, because P is NBR plus NST, you add these two together, yeah, the value will be 204.7 kilo Newton. 204.7 kilonewton. Yeah, that's greater than the value we calculate before. Okay, previously we calculated 125.6 kilonewton. Yeah, this value is greater than this, and this should be a largest elastic load. Okay, but the problem is at this loading, the steel is fail. The steel fail. The steel fail. So even if this is the largest P, but we don't consider this because when you apply this loading, your steel is fail, your material is fail. So this is the final value. So this is the value we want. Okay, we want the largest value. Okay, that means a larger elastic load. Yeah, elastic load. Okay, that means when I apply this largest load, I still I still make the material at the elastic region, okay, because I don't want my material fail when I apply this load, okay. So this is so-called the largest elastic load. When I apply this load, the material is still in the elastic region, okay. If I apply this loading, yeah, the steel is fail. It's not elastic. Okay, okay. So the final answer is 125.6 kilonewton. Okay, so this problem, the kind of you have lots of a lot. You have doing lots of brainstorm for this problem. Okay, so I think this problem really need a demonstration. Okay. Okay, so I just start a video here. So keep working on your mind for this problem. Okay. Yeah, it's not a yeah, because in class I rarely mention this kind of problem in class. So okay, so I just start a video here. Okay, see you in the next video. Okay, bye bye. Okay, good luck. Uh